Hi everyone. I'm very happy to see that you enjoyed the first part enough to actually come and hear about some of the details of how we do goal recognition design. And specifically, we're going to focus here on goal recognition design in deterministic environments. We are going to explore the techniques that together with my colleagues, have developed to solve the goal recognition design problem. Remember, we had this airport, we had passengers that were entering the airport, and we were trying to understand whether they were going to the goal on the right or the goal on the left, goal one or goal two. And we were first evaluating a goal recognition design model using what we call the worst case distinctiveness measure, which measures the maximal progress an agent can take without its goal being revealed. And then we used design to promote early goal recognition. So we're going to dive into the details of how we solve this problem. First, we're going to give some background on automated planning, because these are the techniques that our tools are based on. Then we're going to give a formal definition of the goal recognition design problem. And we're going to show you I'm going to show you both how to compute worst case distinctiveness using compilations to classical planning, and how to minimize worst case distinctiveness using strong stubborn set as a guarantee for safe pruning. So we're going to use a search in the space of design options, and we're going to use strong stubborn sets to guarantee that the solution that we get is going to be optimal. So, um, domain independent planning, what is that all about? Where we have different types of planning domain formulations, but the classical formulation, which is maybe the simplest type of planning, is the one where we have an initial world state, we have some desired goal condition, and we have a set of deterministic actions that agents can perform in that system, in the system. And we have different ways to describe these models, but usually our popular approach amongst planning researchers is to use a compact representation using a language we call strips, where we have a set of Boolean propositions or facts that are used to describe a world state. And a goal condition is a subset of P, so the facts that are true in some states. And for example, if I have, these passengers, so I know an agent is in location 1-3, that would be a proposition. And an action is a triple where we have three conditions that need to be true that are a subset of the propositions. So the propositions that need to be true in order for the action to be applicable, we have the add effects, which are the propositions that are added to the state of the world when some action is performed. And then we have the delete effects, which are propositions that are deleted from the world. So for example, if we have a move action that, well, let's say, from moving from position 1-3 to position 1-4, the agent as a precondition needs to be in position 1-3. After the action is performed, the agent is in position 1-4 and is no longer, the delete effect is that it's no longer in position 1-3. And what we want to find is a solution that is a sequence of actions that transform the world from the initial world state into a goal state. And the solution is optimal if it minimizes the sum of action costs. And there are, as I said, different models for planning that account for various forms of uncertainty. For example, we have stochastic actions, which model the world as a Markov decision process. We have conformant planning, which assumes that the agent doesn't have any observability. We have contingent or partially observable planning that take into account the fact that agents are partially informed. We're not going to cover this today. And as I said, William was supposed to cover these kinds of model in his part of the talk, which isn't going to happen today, but we will include the slides on our website so that you can think about these models as well. So we are here thinking of the strips planning problem with full observability, and we have a 5-tuple description of a planning problem. We have, as we said, the set of propositions. We have some subset of these propositions, which is going to be our initial state. And we also have a goal condition, which is, again, a subset of the proposition that is going to define the goal state. So the conditions under which the goal is achieved. And we also have a set of actions that define what it is that can be performed, as well as a cost that is assigned to each action. Now, I just want to note here that we have these closed world assumptions that anything that is not, the propositions that are not part of the world, of the state of the world, are assumed to be false. So everything that is true is part of the world state, and everything that is false is not. Okay, that's the assumption that we're making, and what we're looking for is an action sequence that leads from the current state, from the initial state to the goal, and we consider this the cost of the action sequence as the sum of the cost of actions, and we want, of course, a solution that minimizes these costs. So the classical formulation of the planning problem implicitly induces a directed graph that can be explored in order to find a solution from the initial state to the goal state. And in theory, we can apply breadth first search if this is a uniform cost setting, or Dijkstra if this is a non-uniform cost setting. But of course, what we care about here are large problems where we can't expect to find an efficient solution using exhaustive exploration techniques. And so not only do we want efficiency, but we also want a solution that is domain independent. Of course, we are giving this airport example just as an illustration, but what we want here are generic tools that would apply to any kind of domain that can be modeled as a classical planning problem. So in order to achieve efficiency, there are different ways that we can do that. And there are different techniques that have been applied in the literature to achieve efficiency. Two major approaches that we have been using in our work are pruning and heuristic estimations. So pruning basically cuts part of our search space, right? We're searching here for a solution. We're trying to figure out what is the best design for our problems, right, for that. And we want to be able to ignore part of the search tree. So we can apply pruning, and when we apply safe pruning, it means that we can provide a guarantee that at least one desired solution is not pruned. That's pruning. And that allows us to ignore part of the search space. Heuristic functions, and this is not to be confused with heuristic algorithms, heuristic functions give us estimations of the value of a specific node in our search. So we want to use heuristic estimations to smell good directions in which to pursue our search. We require these heuristics to be admissible in the sense that they underestimate the cost to goal, and we want to be able to automatically extract them from the problem description. We don't want to, we want these heuristics to be both informative and easy to compute. And of course, this is the trade-off that we need to consider. The more informative they are, the harder it is, and the more expensive they are to compute, and vice versa. But in the benefit of, the power that we get by adopting this approach is that there are many domain-independent solvers and heuristics that have been developed over the past 20 years and that we can use once we can formulate our problems as classical planning problems. Okay, so remember that this was a background on planning, but what we care about here is goal recognition design. So let's formally define the problem that we care about here. Well, we have in a goal recognition design problem, as we said, we have two main elements, main components. The first is the goal recognition design model. And the second is the design model by which we apply changes to the environment and thinking about the measure that we want to optimize, we can think of the different ways in which we can achieve it. So the environment in this case is defined as a planning model that we've just seen. And we also define the agents that are active in the environment. So we, for example, define whether these agents are optimal or suboptimal. This is the place where we kind of define and characterize our agents. We also have a recognition system, a definition of the recognizer, and what is the observability of the agent that that observes the agents and tries to recognize their goal. In addition, we have the design model that specifies the possible modifications that can be applied, the modification transition function, how does a model change when a specific modification, oh, sorry for that, a specific, sorry, fix this in a minute. I'm not sure what happened, just a second. So hopefully you're back and everything is fine. I had some technical issues here. So the design model defines what it is that we have, the ways by which we can change the environment. The modification transition function defines the change that each, the effect of each modification is on our model. And we may also have some design constraints. For example, we may have a budget that limits the number of changes that we can apply, or the cost of the design interventions that we choose to apply. We already said that we have an observable, some observation sequence that we observe. But since we have partial observability by the observer and may have partial observability, we call this the observable projection. So we have to take into account that the sensor model of the observer defines what it is that is observed. And so this is what we are analyzing. And a path that an agent follows is considered to be non-distinctive if it has an observable projection, which is also the observable projection of a path leading to a different goal. Otherwise, it is distinctive. So a non-distinctive path is one that cannot be associated to a specific goal. And this is, of course, what we care about here in goal recognition design. We want to be able to minimize the maximal length of a non-distinctive path. And this is the worst case distinctiveness measure that we've seen before. So the worst case distinctiveness measure measures the length of the maximal non-distinctive path. And since we are talking here about partial observability, it can an agent can perform some actions without being observed. So it's the length of the non-distinctive path can be long, because we can have it can be much longer than the observation sequence that we observe, because some actions are not observed. So we need to account for that when we analyze the goal recognition design model. So going back to our very simple example, in this case, the observable projection and the path, because we had full observability, the non-distinctive path and the observable projection of this path are the same. And this is the case where an agent walks into this terminal, takes the path all the way to the opposite wall, and only then turns left or right. So the worst case distinctiveness in this case is 4. Of course, if we had partial observability, and for example, the observer couldn't see anything on column D or column B, then the worst case distinctiveness would have been 5. So we need to we will think about that when we do our worst case analysis. And as we said, we have 2 tasks in goal recognition design that we need to think about. The first is finding computing worst case distinctiveness. And of course, the basic approach, the baseline approach to finding this maximal non-distinctive agent path is to check all possible behaviors and select the maximal one. So we just explore all the possible plans and find the maximal prefix. But that's, as you can imagine, not going to scale. So what we're going to do here instead is we're going to use a compilation to classical planning in order to compute the worst case distinctiveness. What are we going to do? The basic idea is going to do the following. Is going to be the following. We're going to find the worst case distinctiveness by compiling this two-goal single agent goal recognition design problem into a single two-agent planning problem. And we are going to call this approach the latest split. And what we're going to do is we're going to have in one planning problem two agents that represent the two possibilities of our single agent. Remember, there aren't really two agents, there are just one agent, but we represent each possible behavior by a different agent. And we make sure that each agent pursues a different goal. Okay, so now we have one planning problem with two agents. Each agent is aiming at a different goal. And what we do here is we allow agents to either act separately or together. So they can walk hand in hand, or they can just take separate actions. And in order to detect the worst case distinctiveness, we give them a very small epsilon discount to performing the same actions together. So by encouraging agents, bribing them, incentivizing them by very small epsilon to act together, we detect the worst case distinctiveness measure with a single call to the planner. So we take the goal recognition design problem that we see before, and we create a copy for each of the propositions for each agent. And we make sure that each agent is aiming at one of the goals, and we allow the agents to act separately or together. And this formulation allows us to use any off-the-shelf planner. And of course, if we want the worst case distinctiveness measure to be accurate, so we need to use an optimal planner. And this this idea will reveal the worst case distinctiveness as long as epsilon is small enough, that it's small enough to guarantee that agents don't divert from optimal behaviors. So the first version only accounted for optimal agents, but later in our later work, and then later versions of our goal recognition design work, we accounted for agents that have partial observability, as well as agents with sub-optimal behaviors. You can look at our work to see extensions of this approach. So let's just take a simple example from our grid navigation domain, where we have descriptions of the different propositions. This is Strip's language that defines, this is a description of a domain that defines the different propositions. These are the predicates. These are the propositions that exist in our world. For example, where is the agent and which cells are connected. And a movement is going to be, as we said, defined by preconditions. Remember, the agent needs to be at the source, and of course the source and the destination need to be corrected, and after it moves, it is in its destination and no longer in the source. And we can have different instantiations of this domain. For example, here we have a 5x5 grid, and the agent is initially in position 2, 0, and we have different hypotheses, so different goals that an agent may pursue. For example, here maybe 0, 4 and 4, 4. That corresponds to goal 1 and goal 2 in our image. And this is the compiled domain. This is how we compile it. Now, instead of a single agent, we have two agents, and the information about the domain is agent specific. And we allow agents, agents start by being being able to perform actions together, but at some point they want to split, and once they split, they just activate this function that indicates that they are no longer allowed to act together. And when they move together, again, there is a precondition that they haven't split yet. When they move together, they pay, this amount. It is the amount, the summary of the two actions minus an epsilon. And when they act separately, which is only allowed after they split, they have to they pay the full price. And using this compilation, allowing the agents, and again, sorry, this is an agent, remember here, and each agent is supposed to reach its respective goal, and they start by not being split, and they split later on. Using this formulation, we are able to find the worst case distinctiveness with a single call to the planner. Okay, so that was the worst case distinctiveness calculation. Now we want to find the optimal design solution. Remember, we have different ways by which we can change the setting, and we want to find a way to, we are seeking for an optimal sequence of modifications to apply to minimize worst case distinctiveness. So the basic approach, again, is to check all possible modification sequences, and in any domain that we may care about, this would not scale. So again, we are suggesting here an approach that will increase efficiently by using what we call, what we've already discussed, which is safe pruning. So we're going to take our space of changes and we are going to make it possible for us to prune part of the search space using pruning. Okay, so what we suggest here is to prune at each stage modifications that have no effect on the worst case distinctiveness path. So when we compute the worst case distinctiveness, we know what the maximal non-distinctive paths are. I mean, there can be more than one pair, but we find the current pair at each computation. And we only prune modifications that have no effect on these paths. Why is this working? Why is this producing optimal solutions? Well, we show in our 2019 JER publication that these are prune modifications form what we call a generalized strong stubborn set. Under the conditions that the setting at hand is independent, persistent, and monotonic non-distinctive. So generalized strong stubborn sets for safe pruning were suggested in the literature by Valmari and by Werlet and Halmert. And the idea here is that what in the original formulations, what they cared about is that for a solvable state, there is at least one strongly optimal plan that is not pruned at every node. In GRD, we don't care about paths, but we care about a design solution. What we want to guarantee that there is at least one strongly optimal modification sequence for which there exists a permutation which is not pruned. Okay, so this means that for every node, the modifications that are not pruned include at least include the first modification in at least one sequence that minimizes the WCD. So at least one optimal solution that is represented by the node. And in order to guarantee this, we need to show that the model is independent. So the application order of modification is not important in that setting. If it is, then this does not, our conditions for safety do not hold. It is persistent in the fact that valid sequences can't have invalid prefixes. So if we prune invalid prefixes, we are guaranteed that these won't be prefixes of optimal solutions. And we are guaranteeing that we cannot add non-distinctive paths to our model. So for example, if we build walls, we are only removing paths. And that is why building walls are non-distinctive, monotonic non-distinctive modifications. Oh, sorry. And this formulation, these guarantees allow us not only to account for our existing goal recognition design models, but also to define new modifications. So for example, this allowed us to add to our, for our bag of modification tools, the ability to add sensors to the environment. So in cases where an agent is partially, the observer is partially informed, we could add sensors to the environment to help the agent, the observer, detect better what agents were trying to achieve. And even if we have full observability, goal recognition can be delayed in various models. So another modification that we could guarantee safe, our approach was, our pruning approach was safe for, was action conditioning. What is action conditioning? You can think of this as a generalization of the removal of actions, where we force a partial order between actions. So for example, if in this case we have this robot that is trying to move these boxes, and we see here the robot, the initial configuration of the robot and the boxes or the blocks, and we have two possible goals. Goal one is for block A to be on block C, and the goal two is for block C to be on block D. And the problem here in terms of recognition is the fact that block B needs to be moved for both of these goals. So what we can do here is constrain the movement of the arm of the robot. So if the robot is only allowed to expand its grip, and if you notice here, the B block is smaller than the bigger blocks, so the robot would need to extend his hand to pick up the bigger blocks. If we make it impossible to contract the hand after we expanded it, it will make it necessary for the robot that needs to move block D. We would need to do for the robot that needs to move block B, we would sorry, I got this wrong. I'm sorry. So sorry. The block that needs to be moved is anyways block D, not block B. So block D is the one that needs to be moved anyway. So what we are enforcing here is the case where when block B needs to be moved, and that's only in the case that goal one is pursued, it will be the first action that the robot will perform, because it knows that once it extends its grip, it won't be able to contract it again. So block B will be the first one to be moved. And this is also the interesting thing here is the fact that this is also relevant for cases where, I mean, this idea can be extended to any kind of setting where we can, instead of disallowing action, here we can't disallow any action and still minimize worst-case distinctiveness. We in a way that guarantees that all goals can be achievable. But what we can think about is just making sure that some actions happen before. So this action conditioning allowed us to constrain the set of possible plans. And again, as I described, we were thinking, and this is work that we've done over the years, we were thinking of different ways to extend the goal recognition design framework beyond the classical formulation. And in our first work in 2014, which was the first work that introduced goal recognition design, agents were optimal. But in later works, we accounted, for example, in our 2015 paper, we accounted for suboptimal agents and still used classical planning techniques to solve the problem. In later works, we accounted for noisy and partial observability, partial sensors by which agents are observed, and still using compilations to classical plannings to solve these problems, and understanding where these and where to place sensors in these environments. So we use sensor refinement as a way to reduce worst case distinctiveness. So if I have cameras, where should I place them? Another interesting variant that I really like is our work that in 2016, we realized that goal recognition design can also be used by the acting agent. So the same kind of techniques can allow an agent to understand how long it can keep its goal ambiguous without diverting from optimal behaviors. And these privacy preserving agents can use our worst case distinctiveness tools and sorry, goal recognition design tools and worst case distinctiveness paths to understand how to behave in order to conceal their objectives. And I mean, this can be important for us as users of various systems, allowing us to use these tools to preserve our privacy. I just wanted to give you here another example where goal recognition design in partially observable settings is possible. So for example, think of this setting where we have a truck that needs to load these boxes, and an adversarial goal is depicted in red, and the non-adversarial goal is depicted in green, and we want to detect as soon as possible whether this agent is adversarial or not. In the full observability case, if the agent picks up the O1, that's the worst case distinctiveness. We kind of, that's going to happen. This is something that's going to happen anyway, but the next action, the worst case distinctiveness is one, but the next action is going to reveal the goal. However, if we have a setting if we have partial observability in this setting, things become much harder. So, we don't know. We wouldn't be able to know how many boxes were picked up in location one. And basically the agent here, the truck here, can actually achieve the goal without revealing the goal, without revealing it to the observer. And this is something that we want to prevent in goal recognition design. So our tools can find the minimal change that is needed to minimize the worst case distinctiveness. In this case, we would place a sensor on object 2, which doesn't need to be collected in order to achieve the green goal. And if we know the truck has left the station without picking it up, we know what the goal of anyway, according to whether this object was picked up or not, we know that this agent, what the goal of this agent is. I hope that was clear and gave you some additional motivations for goal recognition design in security applications. As a final model that I want to show you today in detail is a work that we presented in IJCAI 2020, where we were thinking of goal recognition design in in settings where an observer may have full information, but the agent is partially informed. So here again, we have a setting where we have agents that are acting in an environment, and let's say that they are trying to follow a cost minimal plan to the goal, and they want to try to find a plan that makes as few assumptions as possible about unknown variables. So these agents are partially informed. They don't have full information on the environment, but they are nevertheless able to make plans that they will follow to the goal. For example, if I have an agent here in the initial state, the agent knows what the goal is. So that agent is either pursuing goal 1 or goal 2, but the agent is not aware of where there may be obstacles. And in this case, obstacles are something that an agent can sense when it's in a proximity to either a pit of a Wumpus. This is an adaptation of the Wumpus domain from the Intro to AI book by, sorry, I'm blacking out on the name, but I'll come to it very soon. So there is this Wumpus domain where we have where we can sense a breeze when they're near a pit, and the agent can smell a stench when it's near an agent. So this means that when an agent is in a particular state, Russell and Norvig, those are the authors and they presented the Wumpus domain. Sorry for that. Anyway, so they make So this agent that wants to make a plan will make a few assumptions as possible, but it will only act when it knows the outcome of its actions. So it will, in this case, an agent, maybe an agent that is going to G1 will, let's say, sorry, so not maybe, an agent that is going to G1 under our assumptions, given its initial model, will go up. But the problem here in terms of goal recognition is that an agent that's going to G2 may go up, but may go right. And so this behavior of going up is problematic in terms of goal recognition and goal recognition design, because this is a behavior that we cannot associate to a particular goal. So this agent will walk up and walk up again. Still, we don't know what the agent's goal is, but now the agent senses a breeze. So it has to backtrack. And now it goes right, and it terminates execution because it doesn't know what the goal, it knows that it has no way to achieve the goal, and it terminated execution without revealing its goal to us. So in this case, the focus is here is not whether the agent achieved the goal, which it couldn't, but whether it revealed the goal. And no, it terminated here execution without revealing its goal to us. So in this setting, our actor is a partially informed agent, modeled as a contingent planner, and it collects information from the environment via sensors, which are conditions C under which the true value of L is revealed. And the recognizer has perfect information, and it can selectively reveal information to the actor in order to recognize its goal as quickly as possible. So it recognize the actor's goal as soon as possible. What we can change here is the information that we reveal to the actor. So sensor extensions are information items that we reveal to the actor in order to minimize worst case distinctiveness. So we call this information shaping problem the selection of information to reveal to the actor in order to minimize worst case distinctiveness. Okay, and this revelation of information can either be direct, and maybe I have a way to communicate with the actor and say, well, 2-2 is safe, for example, or it can be indirect by placing sensors in the environment and, for example, allowing the agent to sense a stance at cell 2-2 when it's 2 blocks away, rather, at a cell that is further away. Now, let's say that here, I decided to reveal that cell 3-1 is safe. This will encourage an agent that is aiming to G2 to prefer the equidistant plan. Instead of going up or thinking about going up, it will go right, because now it has additional information about that path. An agent to G1 will still go up, and now we achieved worst case distinctiveness after the first step. Okay, and again, remember, we are not thinking here about execution of the plan, because still both agents will fail, but now we know what their goal is. Of course, if we reveal more information, for example, we also reveal that cell 313 is safe, we're back to our initial worst case distinctiveness. And this means that information is non-monotonic, which we've discussed before, and it means that we need to very carefully apply our modifications. So we need a different approach than the strong stubborn sets approach that we used before, which we allowed us to prune modifications that couldn't affect the worst case distinctiveness, that didn't affect the worst case distinctiveness path. And here, what we do instead is apply a different approach to pruning. Again, because our modifications here are non-monotonic, we have to think about a different approach to pruning. And what we do here is take the partial observability problem of the agent and use a compilation from partial information planning to fully observability or to classical planning suggested by Bonet and Geffner in 2011. And we extract the causal graph from the problem definition. So we have an automated way to extract an encoding of which information is going to affect the behavior of each agent. And we can prune all the behavior that doesn't appear in the causal graph. So all the information, sorry, not the behavior, the information that doesn't appear in the causal graph is something that we can safely prune, because that will not affect the agent's behavior. So for example, let's take this example where we have the WUMPUS and we have now the WUMPUS domain. We have the same setting that we described before, but now we have different keys that need to be collected before a goal is achieved. The agent does not know initially where the keys are, and we want to make sure that we prune irrelevant information. So in this case, we know that information about key 3 won't be relevant, won't affect goal recognition, and is not part of our goal recognition design solution because it's not relevant to achieving the goal. So in terms of applications of goal recognition design in partially observable environments, we can apply this kind of technique for any goal recognition settings where we can actually change the information that agents have about the environment. This is relevant to any domain where the actor is partially informed. Again, assisted cognition settings, intrusion detection settings, and human collaboration settings all think about cases where agents are partially informed, and that is something that we need to account for in our goal recognition and design process. So to end this tutorial, I want to give you an overview of different works that have been done in the goal recognition design under the goal recognition design framework, and that we cover in our survey, in our IJCAI 2020 survey of goal recognition design work. So remember that in 2014, we presented the first goal recognition design work, and it was based on 3 simplifying assumptions. First, it was that the fact that the environment was fully observable. Second was that the actions are deterministic, action outcomes are deterministic, and that agents act optimally. And what we were trying to optimize and what we discussed today was optimization of the worst case distinctiveness. And according to the dimensions that I've described that comprise the goal recognition design work, which were the environment dynamics, the actors types, the observer model, and the approaches to, and the observer model, we characterize the different extensions that have been suggested to the goal recognition design framework since it was first suggested. We also characterize goal recognition design work according to the approaches to design that were suggested. So as a first extension to our first goal recognition design framework, Wailase et al. In 2017 were thinking of a goal recognition design in stochastic environments where we need to think about now in these settings, goal recognition design happens in domains where an agent may fail when it's trying to execute an action, and we need to think about the fact that when something occurs, it wasn't necessarily the intention of the actor that occurs. So and also our analysis of the worst case distinctiveness needs to take the stochastic nature of the environment into account and think about the expected cost that may be incurred or the maximal expected cost of a non-distinctive behavior, etc. Mirsky et al. Used a different formulation for the goal recognition design work, where instead of a domain theory, they used grammars, and they used rules to change the environment. In terms of actor types and the variety of actor types that are supported in goal recognition design frameworks, as I said, we offered support for bounded suboptimal actors, and of course for agents that were trying to preserve their privacy. Another interesting extensions was that by Ang et al., where they were thinking of a goal recognition design in a Go game theoretic framework. And Bison et al. And Masters and Sardina were offered the support for adversarial actors that are trying to conceal their objective. And as we described, our work into 2020 was supporting agents that were partially informed. And again, we need to think also about settings where agent from the observer may have partial information about the environment. And we saw two examples for that. So to support partially informed observers, we have a model that accounts for partial sensor coverage and sensor refinement as a way to improve recognition. And in 2020, while Wallace et al. And I was also part of that work, we accounted for partial observability in stochastic domains. Verd and Kaminka supported continuous domains where sensor refinement is applied to support recognition. So how do we analyze the continuous setting in order to support goal recognition? And Bison et al., Marsky et al., and Schwartz, McLaren support a proactive observer, so an observer that can interact and affect the environment while agents are acting in it in order to support goal recognition. In terms of approaches to design, where we can think of an exhaustive exploration as a baseline, and we of course realized that in order to support an efficient solution, we need to think of ways to explore this space efficiently. So as I said, we saw, we formulated the design as a state-based search in the space of modifications, but there have been other approaches to design that have been very interesting. So in 2019, Harman and Simons used NR graph that captured the information about the domain and reveals which actions should be removed from the model in order to facilitate recognition. Sonnet al. formulated goal recognition design as answer set program. I have to say that they were much more powerful than our approaches to goal recognition design, but they only offered a solution for the fully informed case. So fully informed and deterministic cases, and not for our later work. And I hope they decide to extend their approach to more extended versions of goal recognition design. And I et al. Encode the design process as a mixed integer program in a game theoretic setting. So we want to use this formulation to find the best observer strategy for applying modifications to the environment. This is a table that summarizes the different contributions. As you can see, there are the different works and the different parameters or the different dimensions by which we evaluate each of those work, either environment dynamics that changes from deterministic to stochastic actions. We have different actor types, from optimal to suboptimal to adversarial, fully informed, partially informed, etc. We have GRD work that accounts for different sensor models of the observer. It can be fully informed or partially informed. And we have different matrices by which we evaluate a goal recognition design model. We went in depth to think about, we did investigate in depth the worst case distinctiveness, but there are other measures that I think are relevant and that we should explore. And of course, we thought about different design options. So removing actions was only the first approach to goal recognition design, removing actions from the model. But of course, we can think of different ways to modify goal recognition settings and apply goal recognition design to achieve better performance of goal recognition systems in the online. So applying design to support online recognition. Oh, so we made it so far, and as you've seen, there is a variety of very exciting work that is done in goal recognition design, and I can talk about goal recognition design for a lot longer, but it is time to conclude. So I want to leave you with some thoughts. So we saw that goal recognition design is a way to use the design of the goal recognition setting in order to support the online goal recognition process. And while there has been a lot of work in this domain, and it's very exciting, I think there are many other avenues of research that can be explored. So, for example, we can think of supporting both offline and or online design options. So the works until now supported either of these approaches, and not a combined approach. There is a need to support for these frameworks to be applicable to real world applications. We need to think of additional forms of uncertainty we would like to support, and different relationships that can exist between the observer and the actors in the system. And of course, I'm very excited to think about the various applications for which DRD, co-recognition design, is relevant, and looking forward to see development in this field. Thank you so much for listening to this tutorial. I hope I managed to excite you about goal recognition design. You're very welcome to send me an email telling me about any ideas that you may have, and sharing any questions that you may have about my work, or about the survey. And I'm looking forward to interacting with you. Thank you. Thank you so much. Bye.